I'm going to show you how to design a shaft. So to know more about the topic, you can go to Tribauman website, or if you want to listen to the recorded video of this talk, you can subscribe to my YouTube. So this is the case where the problem exists, okay, where a long shaft here is rotating, that required to fulfill this condition where the torque supposed to be 120 Newton meter maximums, and the pulling force here, okay, the shaft supposed to pull the force about maximum of 50 kilonewton with rotation speed of 5000 rpm maximum, and the linear speed is expected to be 150 millimeter per second. So linear speed to the right. So this is the case where you can design this using a belting system like this. Okay, either it can be belt drive system or maybe a motor directly attached to the shaft here. So in this case, we going to determine what kind of power we need for this and what type of motor we need for this. Okay, for this motor here. So let's just focus on the shaft, where we believe the shaft here is the most interesting topic we're going to study. So imagine that we have we simplify the problem into something like this. We have a long shaft here, okay, with to fulfill the requirement of 400 millimeter for in terms of length, and that required to sustain the torque about this 120 Newton meter maximums, and having this force 5 kilonewton, or this linear speed of 50 millimeter per second. So in this case, we're going to focus on the torque and the force here. Okay, what is the diameter for the shaft? I mean, what is the suitable size for the shaft? Okay, first I need to explain to you, shaft size is dictated by torque, not horsepower. So but changes in horsepower and speed, rpm, affect torque. Okay, so accordingly, an increase in horsepower would require more torque, as would a decrease in rpm. Okay, so tips to select proper shaft sizes: one, bigger is better. Okay, meaning that large number of diameter of the shaft size is better, at least it used to be. So meaning that the larger the diameter, the greater the resistance to twisting, okay, due to this torque. Okay, so what we can do is that we can just go online and search, Google search information. First, we go to find the material. So what are the interested material we're going to use for the shaft? So let's say here we're going to use let's choose stainless steel, for example, in this case. So we specifically choose stainless steel AISI 304 solid cylinder shaft with this diameter. So we can choose either 25.4, 28.575, 31.75, 34.925, or 38.1 mm. So all these are taken from this catalog, okay, from this manufacturer catalog available at the website stainlesssteel.com. So referring to this material properties, okay, so we can obtain the general material properties either from the manufacturer website or from the material website. Okay, so since AISI 304 is the most common one, so it's easy to get this material. So tensile strength here is 505 megapascal, yield strength 250 megapascal, with modulus of elasticity of this steel here about 200 gigapascal, and Poisson ratio about 0.29, and this density is 8 gram over centimeter cube. So if you go to this website as well, the manufacturer website, you can get almost similar values. Okay, so in this case I choose from the standard one, which is this one use available online, so MapWeb. Okay, so the next one is that we can also Google search from the manufacturer website, where according to reference number 3 here from this www.plantengineering.com, with articles a relationship of torque and shaft size. Okay, so in this case I pick this equation where it is a relations is a resistance to torsional stress is directly proportional to shaft sizes. So this here is the resistance to torsional stress in unit. So in term this is a power in unit kilowatt, speed in unit RPM, and this give and which directly proportional to shaft size in unit millimeter. So in this case let's choose from refer 1. Let's select D equal, the diameter here is equal to 38.1. so let's see. So if we key in the put in the value here, the diameter, this is the commercially available stainless steel shaft size in the market. Okay, so we use this value, and we know that the requirement from the design earlier, we need about 5000 RPM. So now we can determine the power required for the motor. So then we get the power about 196.8 kilowatt. So in this case we round up and we can choose motor of 200 kilowatt. So in this case I Google search information from this standard motor catalog. Okay, this manufacturer catalog from this website www.teco.com as an example here. So we can from that from this Teco manufacturer catalog, I figure out that we can select an electric motor. In this case we choose, let's say we choose electric motor with power of 200 kilowatts, equivalent to 270 horsepower, that can deliver torque 642 Newton meter. Okay, and but our requirement here is only 120, meaning that this one even far fulfill the condition we got from the problem. So with that I end this talk here. Thank you so much for your attention.